calculating the heat of formation. So let's write our equation first. Let's imagine that we're going to burn some methane. So we've got methane, gas, 2 moles of oxygen, gas, going to form 2 moles of water, liquid, plus CO2, gas. Great. Okay, so looking at this, like any other type of problem, we want to make sure our equation's balanced. And we look at one atom of carbon, 4 of hydrogen, 4 of oxygen. So we're ready to go. Great. So we claim that we can get the delta H of this reaction by just doing the heat of formation of products minus the heat of formation of reactants. So let's do that, and let's actually apply it to this specific example. So one of our products is carbon dioxide in the gas phase form, and there's 1 mole of it, so we just have a 1 as our coefficient. But when we do the other product, water, there's a 2, and we have to account for that, so make sure we don't forget our coefficients. So we've got the heat of formation of water, liquid. And the heat of formation of something is going to be different depending on what the physical state is. So always include the physical state or phase label, like this is gas and this is liquid. Okay, now we have to subtract the heats of formation of the reactants. So we've got the heat of formation of methane in the gas phase. And you might be expecting me to write the heat of formation of oxygen. And if we think about this, the heat of formation is the heat that's absorbed or created or absorbed or released rather, when we make the compound from its element. Well, this is already an element, so that's not a reaction, that's a null reaction. So the heat of formation of elements in their standard state is 0. So just to remind you, a standard state for oxygen is diatomic, not oxygen single atoms. Okay, so there's our equation. So what we can do is look up tabulated values of heats of formation. And heats of formation are tabulated for thousands of compounds, and in any chemistry textbook there's going to be dozens or probably hundreds of compounds with heats of formation. So we can just look these up in the back of a textbook or online or something, and we see that the heat of formation of carbon dioxide gas is negative 285. So you've got a negative 393. So we've got negative 393.5 kilojoules per mole for CO2. And we've got 2 times the heat of formation of water. And that's negative 285.8 kilojoules per mole. And then we have to subtract the heat of formation of methane, which is negative 74.85 kilojoules per mole. And we add all that up, and we end up with a negative 890 kilojoules per mole. And I advise using parentheses because in several cases you're subtracting a negative number. Okay, so here is our heat of reaction for burning methane. And so we can see that if we burn 1 mole of methane, this is how much heat is released. It's negative, it's exothermic. And another way of saying this is that this is much heat as would be released when you used up 2 moles of oxygen gas, right? Okay, so we should check our work to make sure to show you that this actually does cancel, that if we add all these things up, we end up with this reaction. And that's what I'll show you on the next page. So when we say something has a particular heat of formation, we're talking about the heat of a specific reaction where we make the compound from its elements. So for instance, if we wanted to say the heat of formation of methane, that would be making methane from carbon and from hydrogen. And so it's making 1 mole of methane from these things, and everything's in their standard state. So for instance, the standard state for carbon would be graphite. It would not be diamond. That's not the standard state for carbon. And of course, this would be a gas. Okay. If we were to do the same thing for CO2, to make 1 mole of CO2, we need carbon again, once again in the graphite form, and we need some oxygen in the gas form. Great. What about water? Well, if we want to form liquid water, and we were forming these in the gas form and this in the liquid form. So if we wanted to write a heat of formation reaction for liquid water, we'd start off with H2 gas, and we'd have some oxygen. Interesting, when you balance this, we need to make 1 mole of the thing that we're making to make it a proper heat of formation reaction. This is always 1 mole, 1 mole, 1 mole. And that means we need 1 mole of oxygen atoms, which means this has to be a half over here. So at some point, and someone may have said something about, oh, don't have fractions in chemical reactions. That's actually totally wrong. In this type of reaction, you actually have to have a fraction because this needs to be 1 mole. Okay, so these are all formation reactions. Okay, notice that we make 1 mole of stuff and that all of these are standard state elements in their standard state. Okay, so in the most common form, basically. Okay, so let's show that if we can combine these reactions, we can somehow combine them in a way to get the reaction on the previous page. Okay, so we made a claim earlier that the heat of the reaction for burning methane we could get by adding up these heats of formation reactions. So let's add these up and literally write them out to show how they cancel. So first, let's do the heat of formation of methane. So we know that reaction is this plus oxygen going to carbon dioxide. Okay, so that's the first one. We've done this one. And now we need to do this one, and we need 2 heats of formation reactions of making water. So we're going to make 2 moles of water because it's 2 heats of formation. And we just multiply the heat of formation reaction by 2. So instead of half a mole of oxygen, we need a whole mole of oxygen. And instead of 1 H2, we need 2 H2s. Okay, so notice that this is not the heat of formation of water, it's twice the heat of formation of water reaction. Okay, and then we need to have a negative of the heat of formation reaction for methane. So we write, instead of methane being formed, write the reverse reaction. So we start off with methane over here and go to the elements over here. Okay, so the idea is that if we add up all these pieces, we should get our original reaction back. So we're just going to say we're adding these up. We're adding all these things up and seeing what we get. When we add these, we can see, let's go ahead and just add them all up. So we've got carbon, oxygen, 2H2, another oxygen, CH4, going to CO2 plus 2 waters plus 2H2 plus carbon. But notice that there's stuff that's the same on both sides. So we can cancel that just like in algebra. So we can say carbon cancels carbon. And we have hydrogen gas and hydrogen gas. Those can cancel. And what's left? 2 moles of oxygen reacting with methane to form carbon dioxide and water, our original reaction. So that proves that these reactions, if we sum them up in these proportions, will give us our original reaction. And that's all Hess's law is. It's a statement that we can combine reactions to get new reactions, and we can combine them, we can combine their delta H's to get the overall delta H.